Once again, my name is Tanmay Sharma, and I am a TA in this NPTEL course, Power Plant Engineering, and I welcome you to this course, the problem solving session. So the questions here I have referred from the book Power Plant Engineering by P.K. Nag. Now let us move on. First, actually, I want to jog your memory regarding how gas turbine works. So basically, it works on Brayton cycle, and here I am showing you the schematics. Let me show you by pointer. So what happens is that the air is inlet to the compressor. The compressor compresses the inlet air, and this compressed air moves to the combustion chamber, wherein the fuel is also supplied. The air fuel mixture is then burnt. The combust air, which is having a higher temperature now, the hot gas is now hot flue gas is now supplied to the turbine, and inside the turbine the hot gas, it expands, and while it expands it generates power, and this power is partly used coupled with the compressor to run the compressor, and also it is rest of the power is being delivered to the generator, and the expanded gas is exhaust out of the turbine through this channel to the ambience. So there are two types of gas turbine. One is the open cycle and the closed cycle. So in open cycle it is exhausted to the ambient or the surroundings, but in the closed cycle this the flue gas which is it is circulated inside the circle, and the fuel it basically heats up the flue gas externally. It is not mixed with the fluid that is flowing in the cycle. So this is, I will be talking about open cycle gas turbine. So this is the schematic for an open cycle gas turbine, and this is the temperature entropy diagram of the same. So basically the process 1, here the air is being inlet to the compressor, then the compressor compresses the inlet air, but generally the process is isentropic, but due to some losses, friction losses and everything, it and depending about the compressor efficiency, so the process is it finally leads to an increase in entropy. It is not isentropic anymore. So the process shifts from 2s to 2, and you can see the difference between 2 and 1, that is the work done in the compressor, it is increasing. But here again there is one more advantage, so I will talk next. First let me show you the combustion process. The combustion process is 2 to 3. So 2 to 3, it is being done in the combustion chamber, where the heat is being supplied in terms of fuel. So the fuel is mixed with the air, then it is combusted, and the hot flue gases suddenly the temperature has risen, and the energy of the whole flue gases has risen from 0.2 to 0.3. So this is the this is where the heat addition takes place in the cycle. So you can see that initially, if it would have been an isentropic cycle, the process would have started from 2s to 3. But now, since it is not isentropic, rather there is some increase in entropy due to the friction losses and other losses. So the point is shifted from 2s to 2. So a lesser amount of heat needs to be added now. So this is a small advantage, rather to see if it compensates somehow with the additional work done on the compressor. So the heat addition is less required for a non-isentropic or practical process. Then the hot gas, it basically is supplied as an inlet to the turbine at 0.3. So this is the maximum temperature of the whole cycle, and this temperature is basically also controlled because the turbine, the material of the turbine, it is having its own limitations to withstand a particular temperature. So the fabricated material, so it might not be able to withstand beyond a particular temperature range. So this particular temperature is quite significant, and this is controlled. Then in the process 3 to 4 happens inside the turbine, where the hot gas now expands, and it imparts the kinetic energy, the hot gas, the kinetic energy of hot gas to the turbine blades, and accordingly the turbine blades moves. So here also there is a efficiency associated with this process, so that is leading to an increase in entropy, and it is not making the process isentropic as it is theoretically assumed. So the process now moves from 3 to 4 rather than 3 to 4s. So here at this particular temperature, you can see that difference between the highest temperature, inlet temperature, and the final temperature, it has decreased. So the work done inside the turbine, it also now decreases. So then from 4, it is the hot flue gas now exits the turbine, as you can see here. So from point 4 it exits, and it exits to the ambient, where it the gases lose the heat. So this Q2 energy is the heat rejected at the ambient means at the outside conditions. So generally what done is that at point 4, since the temperature of the gases is very high compared to this point 2, right, this is the outlet of the compressor. So what we can do is that we can also utilize this energy of the exhaust gas out here, the flue gas out here, and to increase the temperature of this the compressor outlet, air at the compressor outlet, so as to the air can be supplied at a very high temperature, so that the cool heat addition required will be less, and it will also impact at the efficiency. I will talk about it next. First, since the process here is adiabatic, so we will have to consider this temperature and pressure relations, and let us talk about this first. So you can see that T3 divided by T4s, that is isentropic process, reversible adiabatic process, and T2s and T1, so that is also isentropic, and these are related by this particular equation, that is P2 by P1 to the power gamma minus 1 by gamma. So this is Rp, that is the pressure ratio, the highest pressure by lowest pressure. Then the work done is basically external work. So it is given by this equation, and you might be reading this about this in thermodynamics courses. Then I wish to talk about how we are getting this work done, and one of the most interesting things here, that is this PV can be converted into MRT T1 minus T2, and we get a particular relation like this. So gamma R divided by gamma minus 1, this basically represents specific heat capacity at constant pressure, so that is Cp. So although the work done is generally this formula is applied in 1 to 2 or 3 to 4, you can see that these are not constant pressure processes, but yet we are getting a term like this, so we can use this Cp term at the inlet conditions to calculate the work done in each cases. So normally we cannot use it because there is a change in pressure and Cp changes with pressure, but since while deriving we are getting a term Cp, so we will be considering it. Accordingly, we can now write the expressions of the turbine work, that is Ma plus Mf into Cpg T3 minus T4. So here Ma and Mf means the Ma is the mass of air inlet to the compressor, and Mf means the mass of fuel that is being supplied to the combustion chamber. Cpg is the specific heat at constant pressure of the gas mixture, that is the fuel as well as the air. The gas mixture will have a different value of Cpg, so that is being considered in the turbine work. And compressor work, it is simple, it is only utilized for compressing the air, so we will be considering only the mass of air into the Cp of air into the temperature difference, that is T2 minus T1. Then heat added will be since we are heating both the mass of air and the mass of the fuel, so we'll be considering the mass together, and the Cpg will be this and T3 minus T2. So this is a constant pressure process, because along this pressure, these are constant pressure lines, along this constant pressure lines it is happening, so it is a constant pressure process. But somewhere if the pressure loss is happening, you might see in a practical case the pressure loss will also happen. So this curve will shift something like this, not exactly here, but to decreasing pressure at higher entropy. So we are not considering that at this time now. Then heat rejected will be, since the turbine exit will contain both some air and fuel, so that will be Ma plus Mf into Cpg into T4 minus T1. Okay, so T4 minus T1. So why we are considering this? Because T1 is the inlet conditions of the air entering the compressor. So the total energy that the flue gases exiting the turbine has will be compared with respect to the inlet conditions of the ambient, right? That is why we will be considering Q2 as 4 minus 1. But the Q2 value is not utilized in any of the expressions, so you need not worry much about it. So finally we'll be calculating the efficiency by this formula, since the work generated in the turbine is also utilized in driving the compressor. So we'll have to consider the net work divided by the heat supplied. Again, now since the process is not isentropic, so the process shifts from 2s to 2, and we need to supply a little bit lesser amount of heat, right? So the Q1 decreases due to the isentropic processes, and the efficiency slightly increases due to this isentropic process. And the isentropic process happens because while compressing, the air gets heated up due to the friction. That is why it is gaining some energy in here from 2s to 2. So this was about the process and analysis of the Brayton cycle. Now let us solve one problem. So this problem I have taken from the book Power Plant Engineering by P.K. Nag. And this problem actually talks about intercooling. Now what exactly is intercooling? Also regeneration. I will briefly tell you about this. So intercooling means there are two compressors. There can be 2, 3, 4 compressors also. Between each compressors, the temperature of the outlet of the compressor is cooled down, and this lower temperature, as you can see. So the outlet by this, although the pressure is rising at the compressor, the with pressure the temperature is also rising, right? So the temperature is then cooled down at the same pressure. Again, this compressor rises the pressure at from a lower temperature to that particular temperature. So you can see from this TS graph, it will be better here. So from 1 was the inlet to the compressor 1, so 1 to 2 it is going, and then again it is being cooled down from 2 to 3 in a constant pressure process. Then it again enters the compressor 2 at 0.3, so this is 3 after cooling. Then it is again the pressure is risen, but the temperature, you can see the temperature rise is almost constant. The temperature in fact for perfect intercooling, these temperatures, the 2s and 4s and 4 and 2, this will be almost constant, exactly constant. So exactly equal. So what happens is that by this process we are not increasing the cycle efficiency. Let me guess, right? The cycle efficiency is not increased, because in the cycle, initially the cycle would have been from here to this, means directly if we compress it till point this, and then consider this particular area only, so that would have been the total area under the cycle. But now we are increasing the area, also the increasing the heat addition. So if we are not considering any regenerator, we are increasing the heat generation. So by that, what happens is that the cycle efficiency decreases. But what is the advantage? The advantage is that if we consider a regenerator, so what is a regenerator? A regenerator is basically, it utilizes the energy which is of the flue gas which is exiting the turbine. So the flue gas exiting the turbine is a quite high temperature, it is having a lot of unused energy. So that energy is being actually utilized to heat up the air which is leaving the compressor. By that we can we can actually utilize a lesser amount of heat, but the main thing is that the heat recovery, the amount of heat energy that is being here utilized, uh, means leaving the turbine unutilized, that can be utilized in adding the heat out here. So the heat recovery process, it basically is uh, it is a plus factor in this kind of conditions, intercooling. So in our question, so we have a intercooler, and it is a perfect intercooler. That means there is a particular ratio, this there is a particular expression for what should be the P intermediate pressure. So the final pressure is this P2 and initial pressure was P1, but there is a intermediate pressure. So for this, there is a particular condition of the intermediate pressure that should be the root over P1 into P2. Okay, so that is corresponding to 2.45 bar, and uh, in a perfect intercooling case, the T4s and T1, T3, T2s, T4s, T2 and T4, everything will be same. If yes, obviously, if we consider the efficiency of each of the compressors is constant. Okay, the T4s, T2s will be constant. T4 and T2 will depend upon the efficiencies of each compressors, and accordingly, if these are constant, then the T4 and T2 will be equal. So the first thing in this kind of problems, so first let me read out the questions. So here it is saying that it consists of two-stage compressor with intercooling and a single-stage turbine with regenerator. Okay, there is intercooling and regenerator. Air enters the compressor at 1 bar 20 degrees Celsius. So here it enters and it is at 1 bar 20 degrees Celsius. The maximum temperature of the cycle is 900. So I'm telling you that the maximum temperature is being controlled due to the there's some material issues. So that is why it is controlled. Then the maximum pressure ratio is 6, so 1 bar, and the pressure ratio is 6, so the final pressure is 1 into 6, so 6 bar. Then the effectiveness of the regenerator is 0.7, so this is the condition of the effectiveness, which I will explain later. The rate of airflow through the plant is 210 kg per second. Okay, air flow rate is given, and the calorific value of the fuel is given as 40.8 megajoule per kg. Isentropic efficiency of both compressors is 0.82. Since the efficiency of the compressors is equal, so we'll have 4s and 2s equal, then temperature at 4 and 2 equal. And the combustion efficiency is combustion efficiency is 0.95, that is at the combustion chamber, and the mechanical efficiency is 0.96. Okay, so that will come after here. So take for air the Cp for the air is given, and the gamma is given, and perfect intercooling and neglecting pressure, the heat losses, estimate air fuel ratio, cycle efficiency, power supplied by the plant, and specific fuel consumption of the plant and the fuel consumption per hour. So for these kinds of problems, it is always very useful if we can get all the temperature points. So basically all the equations are related to the temperature difference. So if we can get the temperatures of this 2, 4, then 6 and 7, then we can find out easily the all the work done and the heat supplied, right? So we will first try to find out the temperatures. So we'll use this equation, the adiabatic, since this is an adiabatic process. The first stage is 1 to 2s, the isentropic process if we consider. So by that we will get the temperature at 2s to be 378.59 Kelvin. But since it is not isentropic, so we'll have to consider the efficiency of the compressor. Now the efficiency of compressor is defined as the T2s minus T1. So this was the least amount of work that was supplied to the compressor, but instead it is taking higher amount of work, T2 minus T1, right? So that is how the efficiency is defined, and utilizing this formula we will get the temperature value of T2 397.38. okay, so T2 is we have found out, but since it is perfect intercooling, T2 and the compressor efficiencies are constant, so same will be down here also, and we will find that T2 and T4 will be constant. Then it is almost constant, you can see here also. So I have just to explain you, I have shown here also. So for the P2 and PI, I have considered the same thing. 4S I have got as 378.74, and utilizing the compressor efficiency I have got 397.32 Kelvin. So it is almost close. That can be considered almost equal, right? So T2 and T4 are almost equal. Then we have got T2, T4, okay. Then we will calculate this T6, we know. T7 we need to know. So T6, T7, this is adiabatic process. We will again do P2 to P1. There is no intermediate pressure in this turbine expansion process. So directly we will get the value of T7s. But again, T7s we have got, but it is not isentropic. So we will have to consider the efficiency, and accordingly we will get the temperature T7. So that is this point. So from T6, that is I think 900 Kelvin, so it is being expanded up to this 785.84 Kelvin. We got all the temperature points, right? Okay, we will have to consider the regenerator also. So regenerator, what it does is that it utilizes the energy from T7 flue gas from T7, and it heats up the air leaving the compressor. So the effectiveness will be given as such, the actual, which is the temperature rise it is causing, whereas what is the maximum temperature rise. So maximum temperature rise would have been, so since we are heating from 7 to 4, right, so we are utilizing this amount of heat, T7 minus T4, but this is the maximum temperature rise it can give, but rather we are getting T5 till only T5. So T5 minus T4 is the only heat gain that we are getting. Okay, this actually this diagram is not up to the scale, otherwise the T5 would have been below this T7 point, somewhere out here. Okay, so this is how the effectiveness is defined, and the T5 accordingly this point is given as 669.28. So the air is being heated from 4 to 5, and after that the combustion is happening from 5 to 6. So we'll have to consider all this now. So how to make the energy balance? So total energy balance will be the mass of fuel into its calorific value into the combustion efficiency. So not the 100% of the combustion is not fruitful, right? So there will be some losses, and accordingly we'll have to consider them. And this will be CPG, but the CPG is not given, so we can consider it for air. So it is not that different. Normally CP is 1.08, and so 1.005 also it is taken, but the normally for CPG it is 1.2, so not too much difference it is giving, so we can consider directly CP as it is nowhere given. Then 1 plus MF, so MF is per kg of the air input, so we are taking, and into T6 minus T5, so this is where the combustion is happening, heat addition is happening. So T6 minus T5, and we will get the mass of fuel. So we do not know the mass of fuel being added to increase the temperature from 5 to 6. So that is after solving this we will get mass of air to be 0.013 kg per kg of air. Per kg of air it is being calculated. So we know the air fuel ratio is the mass of air divided by mass of fuel, so simply we will divide it and we will get the air fuel ratio. So this is the amount of air fuel ratio we need for this process. Next we will first calculate the work done from the turbine. So work done from the turbine is T6 to T7, right? So T6 to T7, and it is CPG, so simply 1.08 we are considering, and this time both air and fuel is being expanded together in the turbine. So the whole process will have this if we consider MA to be 1 for now, so that is 423.67 kilojoule per kg of air. Then the for compressor also same T, but then there are two compressors, so T1 to T2, again T3 to T4. So we'll do but the air is constant, right? So this is the first part, this is the second compressor, Accordingly, we'll get the work required by the compressor, that is 209.74 kilojoule per kg of air. The net work done is 213, this deducing the compressor work from the turbine work, 213 kilojoule per air. Heat supplied will be directly from the mass of fuel we can get, so using the combustion efficiency and calorific value, and this is the amount of fuel per kg of air. So we will get, this is the amount of heat supplied from 5 to 6 heat supplied. So total cycle efficiency will be 41.7%. Okay, then the second thing is we'll have to calculate the power supplied by the plant. The power supplied by the plant, it is if the air flow rate is given 210, we'll simply multiply, and there are certain efficiency associated with this also, right? The mechanical efficiency, then combustion efficiency also. So you will have to consider all this, and to this is the amount of power leaving the plant. Then the fuel consumption per hour is given by this particular formula, MA divided by air fuel ratio into 3600 to convert it into hour, and we will get this particular value of fuel consumption per hour. And specific fuel consumption is power output divided by fuel consumed. So dividing it, we will get in terms of kg per kilowatt hour. So this was the problem that we had for related to Brayton cycle. Now as a next topic, I want to talk about Pelton wheel. So let us quickly move on to the, we do not have much time. So Pelton wheel, basically you can see here, this is how the Pelton wheel looks, and it is a tangential flow hydroelectric turbine. So hydroelectric means there is no steam impinging upon the blades, turbine blades, but rather it is this water which is at having a very high kinetic energy, so that is being impinged upon the turbine blades like this. And so these are the blades that you can see, and the particular shape of these blades, this is having this particular shape you can see here. So there is a section which is dividing the two sides. So there is a particular reason behind this, why it is being divided. So this basically it splits the jet. The jet actually directly impinges upon the center, and it splits the jet in both the direction. Okay, in both the direction it splits it. So by that, what happens is that a symmetric velocity diagram from both the sides is so the velocity here and the velocity coming out in here, both the velocity diagrams will be same. Okay, and it will cancel out the axial velocity. So axial velocity meaning the velocity of the jet in this upward direction, okay, axial direction, and again in the bottom direction. So both will be same, equal and opposite, so it will cancel out the axial velocity components. And hence now you can see here, if I what I can do is that if I supply the this jet in tangential direction, so the water will move out in this direction and in this direction. Okay, so that is along this shaft, this longitudinal directions. So if there is any velocity component in the shaft longitudinal direction, okay, so it will impart a particular thrust on the shaft. So if that thrust is present, it will have some vibration effects also. So that vibration effect is basically cancelled out. It is simply, it is now rotating and not moving like this. So that is the this advantage of this splitting, this type of arrangement. Then let us focus on the velocity diagrams. So at the inlet, what is happening is that simply the velocity, this velocity is the velocity of the jet leaving the nozzle. Again, inside the nozzle and outside the nozzle there will be some difference, there will be some loss, that is due to the vena contractor that is being formed out here. Okay, so we'll have to consider that that is 97 or 99%, means the velocity will be only affected only to about 3 to 1%. So this is the v1 that we have. Then the blade will also be moving, so the velocity of this um, jet is v1, but the blade is also moving in this direction, that is vv. So we'll have to subtract that velocity to get the relative velocity of the jet with respect to the blades. So the v1 is basically responsible for the whirl component. Absolute velocities are responsible for the whirl component and the axial component, right? So we already discussed the axial component. At the inlet there is no axial component, but the whirl component is the entire v1. Now I will explain you what is the whirl component and what is axial component from this outlet velocity diagram. So at the outlet, when it is coming out, the jet is leaving out the blades. So what is happening is that it is leaving out with respect to the relative velocity. So at the relative velocity of the steam is maintained, okay, and it is coming out with in the velocity of the jet leaving out will be the relative velocity. So this is the relative velocity, and since the blade is moving in this direction, opposite direction of the relative velocity, so we'll have to subtract this vector in here, that is the blade velocity in here. Okay, so if we subtract, we will finally get the absolute velocity. So it depends how much is the inlet velocity. Based on that, whether the absolute velocity will be like this or the absolute velocity will be in backward direction in this. So that would further impact on this calculating the tangential forces and everything. But for now, let us only consider that the velocity is we do not consider the sign. So let us later on we'll be considering the sign, but in this session there is no problems related to that. Now the whirl component. The whirl component is based on the absolute velocity, not the relative velocity. We have also discussed this in the steam turbines. So what happens is that the velocity component of the absolute velocity in the direction of the blade movement, that is the whirl velocity, right? So this is the velocity direction of the blades, and this is the absolute velocity. The component along this blade moving direction is from this point to this point, that is also represented in here, vw2. So here if we consider now in the inlet velocity diagram, the velocity of the blade is in the direction of the velocity of the jet. So this has no inlet angle to the jet, it is directly impinging at without any inclination, right? So the whole of the velocity at which it is impinging, that is the whole of the absolute velocity is the whirl velocity. That is why the vw1 is entire v1, but here it is a bit different, vw2. So again there can be some friction also in this blade. Here if you see, when the water is gliding over this blade, so it will face some friction and the velocity will be reduced. So the relative velocity at the inlet may not be the relative velocity at the outlet, so vr2 will be somewhat less than vr1. So that is the friction loss coefficient k. So we'll have to include that in our further calculations. Then if we calculate the velocity whirl component at the outlet side, so that will be simply vr2 cos 180 minus theta. So 180 is the angle by which it is deflecting the jet stream. So jet is being deflected in this way, right? That this is the total angle of deflection, that is theta. Okay, that is, so we'll have to consider this. So this angle will be cos this theta minus so 180 minus theta, taking the component in x direction, that is vr2 cos 180 minus theta. So that is in the x direction. Again this is in this direction, so we'll have to consider this blade velocity also, and together we'll get the whirl component velocity. And So this is the world component velocity. Then world component velocity. So you can see from this diagram also the basic thing, the v r2 cos theta. So that is the whole part, and if the absolute velocity in this direction, so you'll have to subtract the late velocity, so minus vb2. But if it is in this direction, we'll have to again we'll have to subtract that, but the velocity of the world component will be in the opposite direction. So I have written this absolute value, and there is a plus minus sign over here, so it can be either positive, it can be either negative. So moving forward, if we calculate the total work done on the wheel, how can we calculate? By calculating the change in momentum. So this change in momentum is m, but m is not the kg, it is kg per second. So change in momentum with respect to time, that is the work done, right? So this is mv1 minus kvr1 cos theta 1 minus 180 minus theta minus vb. So this since the blade is the world component at here is direct, suppose if we assume it is directed in the opposite direction of the v1, so we'll have to have a minus sign out here, so total effect will be positive, and this is the total work done here. Okay, then the hydraulic efficiency can be calculated in this manner. So somewhere I'm missing a vb out here. So this is the force, the work done is the whole thing multiplied into the relative velocity, sorry, the blade velocity. The force into velocity will give us power, right? Force into distance divided by time. So we'll have to multiply this whole with the blade velocity, and that will give us the work done on the wheel. And the work done divided by the kinetic energy. What is the kinetic energy? The this half m v1 square, that is the kinetic energy of the inlet jet. That will give us the hydraulic efficiency. Now these are the formulas how it is being derived, and let us try to use it in some of the problems. So the first problem is a Pelton wheel driven by two similar jets transmits, so total 4000 kilowatt is being transmitted to the shaft when running at RPM is given 400 RPM. The head from the reservoir level to the nozzle is 200 meter. Okay, the head means the water is coming from a certain height, right? So the height is given as 200 meter, and that height is actually the potential energy that is given with respect to the this turbine. So the higher the potential energy, higher will be the kinetic energy of the leaving jet, right? So this is a very important parameter. So nozzle is the height is 200 meter, that is the head, and the efficiency of power transmission through the pipelines and the nozzles is 90%. Okay, so we'll see how we can use this. The jets are tangential to a 1.5 meter diameter circle. Okay, the diameter circle is 1.5 meter. The relative velocity decreases by 10% as the water traverses the buckets, which are so shaped that they would, if stationary, deflect the jet by 165 degree. So the deflection angle is given, okay, the theta. Then neglecting the windage losses, estimate the efficiency of the runner and the diameter of each jet. Okay, so first of all, what we can do mechanically, what we can do is that first of all we can calculate the from the head that is given, we can calculate the velocity of the fluid at the inlet to the bucket. So normally in the formula you will see that, so this is the 2gh. Okay, theoretically if I see that the kinetic energy equating to the potential energy will give us the velocity at the outlet to be root 2gh, and somewhere you can see the velocity of the jet leaving the nozzle, it is being multiplied by cv in outside the this means cv to the theoretical value, so outside the square root. But now I am multiplying it inside the square root sign. Why am I doing this? Because the total head that I am receiving, that is the mgh potential head, so that total head is not being completely utilized, there is some losses. So the amount of power transmitted is only 90%. 10% is being lost on the head itself, not the velocity coming out of the nozzle. No, only on the head it is 10% loss. So I will have to deduct the loss inside the square root out here. So this is how it is being calculated, velocity of fluid at inlet to the bucket. Okay, so we are having no loss at the nozzle, rather we are having at the transmission. So that is why we are calculating like this. Then the velocity of blades, okay, the RPM is given, the diameter of the wheel is given, so accordingly we can calculate the velocity of the blades. Then the hydraulic efficiency can be calculated as derived before. Again, there is a VB that is missing out here, so please consider it. So that VB, including the VB, you can find that 2 into so this whole will give us the hydraulic efficiency 93.12%. okay, then so after getting the efficiency of runner, which is the dependent upon the jet velocity, angular deflection, the losses while gliding, okay, then relative velocity loses by 10%, so this 10% is considered. And then this would be 0.1, 10%, sorry. Then and the blade velocity. So all these are basically required for hydraulic efficiency, and we can directly calculate it that in this way. Then we can calculate the total work done by the jets, that is 4000, which is being transmitted to the shaft, but some amount of it is being lost, right? So we have to supply some higher power of the kinetic energy, only then compensating the loss. 4000 megawatt is being delivered to the shaft, so that is why we will divide it by the efficiency. This is the amount of kinetic energy that is coming out from all the jets combined. Okay, and since we have two jets, where it is given two jets, two similar jets, okay, driven by two similar jets, so that is why we divide the whole power by 2, and that is each of the jet is having a kinetic energy of this much power. Then so we do next energy balance in such a way that each of the kinetic energy, so we can calculate by this formula the velocity of the jet leaving the nozzle. So according so if the velocity is known, so we will calculate the diameter of the nozzle that we require. Okay, so by this we get the diameter of the nozzle is 0.1614 meter. So this is how the energy balance is being done, and by the knowledge of this we can calculate the diameter. And but let us now work on a similar problem, which is specifically illustrates a designing of the Pelton wheel. Okay, we have some targets to reach, like power to be developed is 600 kilowatt, net head available is 300, RPM we need is 550, then ratio jet diameter to wheel diameter is 0.1, hydraulic efficiency is 0.85, and coefficient of velocity speed ratio, these are given. So if we know all these quantities, can we determine all these parameters that is further needed? Can we design the Pelton wheel? So let us see. So first we need the velocities. Obviously first we need the velocity. So we have the head. From the head we can get the final exiting velocity from the nozzle. So we have the velocity coefficient. Like I said, in the nozzle there will be some losses, and according to the losses you will have to multiply some factor to the this theoretical value. So that is 0.98 to the theoretical value, that is 75.19 meter per second. So this is the inlet velocity from nozzle. Then the blade velocity is given by this speed ratio f into v1, so accordingly 35.29 meter per second. If you know all these values, we can directly calculate the quantity of water required. So we know the overall efficiency, I think. So so this is the overall efficiency. Since if there is no transmission losses in everywhere, then we can directly consider this. So the overall efficiency is 0.85, and it is given by this formula. And the by this we can have only one unknown, that is the discharge rate, and it is evaluated to be 2.4 meter cube per second. So this way we can calculate the quantity of water required. Then the diameter of wheel, we know the blade velocity, we can directly put it, the d is unknown, so directly we can get d is equal to 1.23 meter. Okay, next, diameter of each jet. So we are given the jet diameter to wheel diameter ratio. Okay, we know now we have come to know the wheel diameter, so the jet diameter will be 0.1 of that, so that is 0.123 meter. Next, number of jets. So the total amount of quantity of water required is this sorry, the numbering is a little bit off. The quantity of the water required is, we know the Q evaluated to be 2.4, so we divide the amount of water that needs to be supplied from each jet. Okay, so by that we will get to know that we need at least 3 jets to supply this amount of water. So this is how we can actually design a Pelton wheel and its various parameters, how we can control the amount of power to be developed. So this was a question regarding that. Now I want to discuss a very important thing, that is specific speed. Okay, so specific speed is basically defined as the speed of a geometrically similar turbine which produces 1 kilowatt power under 1 meter head. So suppose we have a very big turbine, okay, and it has a very big head. So how can we cannot directly experiment on that, right? We can experiment on a very smaller scale, so we have to scale down the whole thing. The geometrically everything is same, but we have to scale down in order to analyze it. We cannot directly go and do experiments on a very big that actual this turbines and dams. That is why this specific speed is a very important property, not property, important parameter that needs to be understood properly. Okay, so suppose so we will have to consider this the whole turbine. So geometrically turbine which produces 1 kilowatt power under 1 meter head, and actual turbine is producing some P amount of power under some H amount of head. Okay, so what is the relation between the RPMs that each of the turbines will be having? So that we'll need to understand. That is the specific speed. So first I wish to derive it in front of you, since it is very hard to get this derivation. So the overall efficiency is the shaft power by net power supplied, right? The net power supplied is basically rho QGH, that is the head being supplied against the turbine. So the power is directly proportional to Q and H. Okay, so after that, now we know that the power is directly proportional to the Q and H, but we need to eliminate these properties. We need to have only speed, power and head, and eliminate all other properties. Only then we can compare, right? So we'll have to do it step by step. So first we'll consider the tangential velocity and jet velocity. So the blade velocity is F into V1, so it is of this directly proportional to V1, the jet velocity. And jet velocity, we know that it is proportional to del H by this particular formula, root over H. Hence the VV is also proportional to root over H by this particular relation, right? Now we know the VV is directly proportional to root over H, but how it is related with the diameter and the speed? So it is related with this particular formula, that is directly proportional to the product of diameter and speed. Hence the product of diameter and speed is directly proportional to the del H, means it is proportional to del H, also it is proportional to D into N. So this is also legit. Then D is directly so by this formula D is directly proportional to root over H by N. Okay, so diameter we know now is in the terms of head and speed, so that is good. We have eliminated the diameter at least. Then we'll eliminate the rate of discharge in terms of H and N. So rate of discharge is given by area into V1, that is jet velocity. So area is basically width of the blade, sorry, width of the this um, the width of the blade and into the diameter. So accordingly we will get that the geometrically, if it is similar, that the B, A and D are having a particular ratio. B is directly proportional to D. Okay, so this ratio needs to be maintained in the actual turbine also. The turbine that we need to scale it down. So this geometrically similar concept should be applicable in both. Okay, so this ratio should be constant. Then A is now directly proportional to D square, and D is this, so we can directly get this particular relation, A directly proportional to H by N square. Now we directly put it, A we know, V1 we know in terms of H and N, so directly put if we put it, we will get Q is directly proportional to H to the power 3 by 2 divided by N square. Okay, so Q is eliminated in terms of H and N, and now we will again focus on the power, the main equation we have. Q we have derived now, so Q into H, if we directly do, then it is directly proportional to H to the power 5 by 2 divided by N square. So now when we are scaling down, what happens is that the power can be somewhere the condition of the turbine will be having a particular power P at a particular h height h, head h, and it is corresponding to a particular speed n. Okay, but we need to scale it down to a particular turbine which delivers power of PS 1 kilowatt at a head 1 meter. So of this particular turbine, and if we consider both the turbines are same, only scale down, then what should be the particular speed to maintain the whole relation, correlation between the two scale down turbines. So for that, PS is directly proportional to this per this formula. Okay, only HS and PS is being replaced. So we will make a ratio of these two. So P by PS we will get, and finally we will get, so PS is 1, HS here it is 1, so only remaining is NS, N and H and P. So finally we will get the specific speed. Okay, the specific speed is equal to N into root P divided by H to the power 5 by 4. So this is a very important property to reduce the scale of an actual turbine to a scale to a very small turbine which is delivering only 1 kilowatt power at a head of 1 meter, so very small, and corresponding to this specific speed. So this turbine will, the scale down turbine will have the NS specific speed. So that is the thing here. By this we can correlate the both two cases. So let us now quickly go through an example. Okay, here which utilizes this concept. So a single jet impulse turbine of 10 megawatt capacity is to work under the head of 500 meter. If the specific speed, so head is given, the capacity is given. Okay, then if the specific speed of the turbine is 10, okay, NS is given 10, overall efficiency is 80%, coefficient of velocity is given, find the diameters of the jet and the bucket wheel. So we need to find the jet diameter and the bucket wheel diameter. Okay, so assume the speed of the bucket wheel as 0.46 of the velocity of jet. So how can start it? So first we know the specific speed, and accordingly we will get the speed of the actual turbine, okay, which is delivering this particular power. So so by this we can get 236.4 rpm. Okay, then we calculate the velocity of jet, so that is 97.06 meter per second, and we assume that the speed of the bucket wheel is 0.46 of the velocity of jet, so we directly multiply the 0.46 into 97.06, rather not multiplying 0.46 to this whole theoretical value. So that is leaving us 44.65 meter per second. Then using this formula we will finally calculate the diameter of the wheel, Pelton wheel. Then the overall efficiency we need to calculate, no, we need to calculate the jet diameter. So from overall density we know the all the parameters except the rate of discharge. So rate of discharge we can calculate from here, but we know that is equal to pi by 4 d square, that the area of the jet into the velocity of exiting the jet. So that if we equate it, we will get diameter of jet as 0.183 meter. Okay, so this is how the questions are framed. So the specific speed is given, and according to that it can be scaled up to any particular turbine of having geometrical similarities. Okay, so this is how it is being framed. And I have one more question for you, but maybe I can quickly go through it. So it is just a derivation to show that the specific speed of a single jet Pelton wheel is about 202 times the diameter ratio. Okay, diameter ratio of jet diameter by wheel diameter. Okay, and the CV, F and H parameters are given, by which we will get this 202. So the specific speed we need to calculate. So first I will just quickly go through the solution as we are running out of time. So we will quickly calculate the rate of discharge by this particular formula. So n is the number of jets, this is the area, this is the velocity of exiting the jets. Then we calculate the power supplied by the water stored in the jam. So the water stored in the dam, it exactly gives us this amount of power, but due to the overall efficiency it gets reduced, hence we'll have to consider this. So finally we keep the equation of Q in here, and P we take in kilowatt. So this is the final expression of the power. Okay, then we calculate the peripheral velocity of B, VB of the Pelton wheel of diameter D, and finally get the RPM at which it is moving, the bucket is moving. So that is based upon the this ratio of speed ratio and the head, total head. Finally we put these equations, the power supply and the head, also the RPM, into this specific speed equation, and this is the whole big equation that we can get. And finally we substitute the values F, CV and H that we are already given, okay, here, and we will find that the NS is equal to 202 into root n into d by capital D. Now n was the number of jets, so for a single jet turbine n equals to 1, so the specific speed is given by 202 times the this diameter ratio. So this was a derivation type of question. So by this I have completed the Pelton wheel till Pelton wheel. So next class maybe I will cover the Francis and the Kaplan turbine, and that was all for today. So is there any question? Yes. So here you mean? Yes, yes. So basically you see the the velocity, if you can see here, the velocity of the jet is in this direction from left to right. Okay, please, left to right. So when it comes out, the relative velocity comes out in the opposite direction. You can see also here the relative velocity comes out in the opposite direction. But if the bucket velocity is very fast, maybe the absolute velocity will be in this direction, in the direction of the jet. Okay, this may be the direction. So if this is the direction, the whirl component will be actually negative in this case, because the absolute velocity in this direction, it will have a component in this direction, in the direction of the jet, so the net difference in the world component velocities will be impacted on the this work done on the this bucket, right? So that is the significance of the negative sign. But now why it is coming, let us focus on that. So the exit triangle is this vr2, then subtracting the blade velocity, okay, and finally we have the absolute velocity. This is the vector addition and subtraction, okay. hmm. From left diagram how this is drawn, okay. So actually this is drawn for the lower part, okay. So lower part, the vr2 is coming from this left to right, so this direction and this direction is same, right? So the blade is moving in which direction, from left to right, so the blade velocity will be from this direction, okay. So maybe the blade velocity component may be up to here or may cross this point up to here, right? So it will depend. So if it is up to here, the absolute velocity will be like this, means from left to right like this, right? Then if it is in this direction, then the world component, that is the in the this direction of the blade movement, so which direction will it be in, opposite or in the direction of the blade, opposite, right? So this is the world component of this inlet jet, and in the opposite direction the world component of the output jet. So the total will be the sum of these world components, right? So final minus initial, so the final and initial in opposite directions, so finally we will get a plus sign between, right? But but if the blade velocity is higher than this component, maybe if due to the theta, if the deflection is a little bit lesser than 165, so it will come out somewhere like here, so the VB will cross out here, right? So the absolute velocity may be out here. So then what happens is that the world component will be in the direction of the blade, so then the difference in the world component will be a negative sign, it will be a little bit less. So this is how it is impacting on the force imparted by the jet on the blade. Because the VB2, or basically it is VB, because there is no change in the velocity, it is in the same plane, so it is VB2 equals to VB1 equals to VB, it is written out here. So if the theta is so 180 minus theta, if it is higher, means theta is it is small, okay. So what happens, it will be here, but the VB, velocity of blade, will be constant for that. So so the velocity of blade will be somewhat out here, and the absolute velocity will come here, okay. There is an optimization, actually this will again impact on the velocity of the blade, but the sign will change accordingly. uh, 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 hmm, 180 minus theta, so actually this is how it is actually written. So even if you take the product, and means the subtraction, but the magnitude is plus or minus, will be dependent upon what is the this value. So if you directly write it like this also, it is no issue. If it is this part is negative, it will directly get impacted on here. Right now it is negative becoming positive, right? But if it is negative, again it will become here negative, because negative will be cancelled. So you can directly write it like this, no issues. Relative velocity, because the blade you're referring to the blade exit, or what? in line with the direction of the blade. Because what happens is that we will finally need at what velocity it is finally gliding over the blade. So that is dependent upon the velocity of blade at which it is moving, and also the inlet velocity. So that is relative velocity if we consider that. Again, at relative velocity, if it is moving, gliding over this, it will exit at the relative velocity itself. So, that hmm, with respect to blade, that is why we consider the angle deflection at the blades. So you see the theta in here, it is being considered in here, right? Okay. Okay. Regarding your, I will send. See to the problem of the Kaplan turbine, and I will post you in the email. Question number 14. I have noted it. Okay, sure. Uh, okay. Thank you. Bye.